Hello everybody. In the last three classes, that is lecture 7, 8, 9, I introduced you to 8086 instruction sets. Mostly we talked about data transfer operations instructions. Today will be the concluding part for data transfer instructions, and subsequently we'll take up arithmetic operations instructions. Okay. So in the data transfer operations, in the last class we started with string operations. So we discussed load s, store s, and move s. Okay, s stands for string. Okay, so in the move s, we saw that we don't have to specify the source and the destination address. Okay, it is the move s command is used to shift the data from one memory cell to other. So the source from where the address, okay, the memory cell address or the source from where the data needs to be shifted will be given by DSSI. So the physical address of the memory would be computed by this, and where this memory will be this data which is fetched from this memory will be stored in a memory given by ESDI. So the next physical address will be computed using this, right? So so now we have three kinds of move: move SB, move SW. So move SB means one byte of data will be transferred from the source to the destination. A move SW, 2 bytes or one word, and move. And along with this transfer, when we write this move SB or move SW, the SI and DI will be incremented or decremented based on the flag register. Okay, so all these things I explained in my previous class. So if you don't, you may want to refer to that for more details, right? We also saw that we can repeat this, okay, right, by putting an right, this operation can be repeated n number of times, because if you have to do some bulk transfer, okay, say set of 100 data from one memory to other, so we can use move s with rep. Okay, so we write rep move s, right, and how many times it needs to be repeated, this command, that is given by loading the appropriate data in the CX register. Okay, so every time once this is done, like the move operation is completed and SI and DI are either incremented or decremented, then the C is automatically decremented, and again it will repeat the because both the source and the destination address are being auto incremented or decremented. So after that the C will be decremented, then it will continue till C is brought to 0. So we can do an bulk transfer. So these things along with an example I had explained in the last class. Okay, so another two variations of the string operations which we saw was load s and store s. In the load s, the source memory is given by DSSI, whereas the destination is only AL, that is the accumulator. Okay, AL, AX or EAX. Now here load s, we need to write an AL, AX or like that, right, because AL or AX will tell the microprocessor that we need to bring a byte or a word. So that needs to be specified. Similarly, store s is for putting the data which is available in the accumulator into a memory, and that memory address we don't have to specify. The processor would compute it based on the data available in the ES and DI. So here also we don't have to specify the source. We just write in a load as AL. So the source address from where the data is being fetched will be computed by DSSI. So these are the things which we learned in the last class. Okay, and then today what we are going to learn is we are going to learn about two new instructions, ins and outs. Okay, so before that, let's just revisit again in out how it is done. So simple in out, and this again I covered in the previous class, where we said whenever so how does this memory organization work? First I place an memory, okay, 20 bit memory address is placed here, and the latch is activated, okay, from the ALE. So now this address is latched out here, right? So in case I want a data from an memory, so I have this memory signal going high, and then based on the least significant bit of the address is also given here. So if it is an 0, the odd bank will be selected, and if it is 1, the even bank will be selected through this CS1 and CS2. So to generate CS1 and CS2, what do I require? Because this is the internal RAM, so I require the memory signal as well as the lower significant bit, least significant bit, right? So accordingly, now suppose I want an because 8086 can work either as an, it can take or write, read or write 16-bit data or 8-bit data. So whenever I am addressing, I want on a 16-bit data, then the best high enable signal also goes high. So in that case, both the chips will be selected. So these are the three signals which are required to select the chip. Okay. Now whenever I am writing an in command or an out command, right, in that case the memory is 0 out here. Okay. So that means this chip select lines don't get activated, and these RAMs, they don't get activated. Okay. Instead these lines get activated. Okay. Now here also, depending whether it is a read operation or a write operation, IOR or IOW gets activated. So now this address lines are available here. The address is available here. These chips are not are selected, but this is going elsewhere also. So I will have an input output port address decoder, which will select the appropriate port, right, and then that data gets transferred onto this data bus. Okay. So that is how in out works. So we saw there are a few commands like in out always happens with the in and out always happens with the accumulator, right? So when I write in, I can define the port number. So from this port, whose address is given by this 8-bit number, so it comes here. If I write an AX, so it is again from the same port, but this port is an 2-byte port, right? It has 16 bits of information available with it, so that would come here, right? And the second option what we have is in ALDX and in AXDX, in which DX, when I say DX, right, the port address will be specified by the contents of DX. Okay, so not that from DX some data is going to come to AL, right? The port address will be given, has to be loaded into the DX register. Okay, and now this is an 16-bit information, right? So 2 to the power of 16 ports can be configured for an 8086, right? So input output ports. Similarly, when I write AX, so what happens is this 2 to the power of 16 bits, some of them could be an 8-bit port. So whenever it's an 8-bit port, I can write an ALDX, and if it is a 16-bit port, right, right, 2 bytes of information can be simultaneously returned into AX register, okay, from that specific port. So these are this is the in command. Similarly, I can have out command, where I specify the port number and I can write AL. So 1 byte of information from AL goes to this. I can't write AH. Okay. So similarly, when I write AX, 2 bytes of information goes into this port. Okay. Out also is similarly here. Out also, the port address is available in DX register. Okay. So this is not data. This is just an indication of the port address, right? So we have now this happens only for a single data transfer. So when we have to do a multiple data transfer, so that is the time this ins operation comes handy. Right. So in ins, here ins also, in the ins command also, the accumulator doesn't have to a role. Okay. Although this is a complex instruction, and the microprocessor actually might be getting the data and putting into accumulator, and then from accumulator it might be transferring elsewhere, right? So that is hardware wise, but for a software engineer you don't have to bother about all those things. When I write ins b, what happens is, okay, so the port address is given by the dx register. Okay, from there this data will be fetched, okay, and it will be placed into the into a memory location whose address is given by es and di, and after fetching that data, di automatically gets incremented by 1 or decremented by 1 depending on the flag register. Again, the role of the flag register we discussed in the last class, and how we can write, and if the flag register is 0, it will be auto incremented, and if the flag register 1, then di will be decremented, right? And we saw we can write clear d, so that flag register would be reset to 0, or we can write store d, in which the flag register, so this will decide the direction of auto increment of d, right? So I can also write ins w, in which now, since it's a word, two datas, okay, 2 byte of information will be brought from this port and stored into di and di plus 1. So obviously, to keep it ready for the next operation, di will be incremented by 2. Similarly, I could have a double word where di increases by 4. Okay, so if I take this example out here, so if I do a move di offset list, so in the di, okay, the offset, or wherever I want this data which is being brought from the port needs to be stored, so that offset location is being fed into di, right? And dx, okay, this is the port number. Okay, so now I have to feed the port number to the dx register. Clear is it auto increments the now we are going to auto increment, right, the di register. So after fetching the first data, it will increase. Okay, now suppose I have to get 50 data from the same port, right, and store it into right, in different memory locations, then I can use the move command, right, and put cx as 50, and I write a repeat instruction, okay, ins b. So what it is going to do is, right, it is going to go first to this port, okay, port which is defined by AC3H, get the data and store it into this location, right, which is given by di, right, es plus di, and then again increase this, automatically increase the memory address, fetch again, go and fetch the data from dh. So so in 50 locations, okay, the data will be fetched from dx, right, and it will be put into 50. Now you might be thinking, what could be the use? Suppose I want to monitor some temperature of a room, so I have put a temperature probe, and I want to keep monitoring the temperature, and probably every 10 minutes, right? So what I can do is I first earmark a memory location. So this is the memory location, this is the port address which is of the temperature sensor, right? This is auto increment, right? And cx I can probably give a large value, and in between, right, I can probably put some delay, right? So we can call for some right, a program which will introduce some delay, so for 10 minutes delay. So those things we will learn subsequently, how to introduce these kind of delays, because otherwise what happens, after the soon after this execution, it will again go and fetch the next data. So depending on the clock frequency and the number of cycles which are required to complete this instruction, continuously that data will be picked up from the sensor, right? So if it is suppose 50 megahertz, so 1 by 50 megahertz is the right, time taken for one clock, and to do this entire instructions, okay, suppose it is taking 10 cycles. I'm just giving an example. So whatever is the time computed, so say for example this comes 10 divided by 50, right, megahertz, okay, so that comes out to be 1 by 5 megahertz, okay, so a few uh, few microseconds or something like that, okay, or few nanoseconds. It is going to keep getting data from the same port, and in subsequent memories it will keep writing. So that may not be of an unless it is very critical data where you have to keep logging at every microsecond. Then and then your memory will get filled up, right? So that may not be a very ideal situation. You might want to monitor in real life situations only once in a, because it is going to every time it's going to fetch the data from the same source, and in consecutive memory locations it's going to fill that data. So you might want to introduce a delay in between, okay, that we will see as and when we come to that, okay. So that is one. Or you could say maybe there are hundreds temperature sensors, okay. So in that case each I want to get this data and put it into one memory location, get this data and put it into this memory location, right, from each sensor. So in that case probably I need to write here, right, and I can increment this data in the dx, right. So every time I can write dx is equal to dx plus 1 or something like that, where so that the next port data is fetched from the next port. So those things of modifications we can do. Essentially what ins does is it gets the data from a port whose address is given by dx, and it feeds it into esdi, okay, and pushes the data into exdi and increases the value of di, okay. Now how you want to use it for a specific application depends on that. And along with rep instruction ins b, what you can do is you can repeat this instruction as many times as you need by putting the appropriate value in the cx register. So every time after doing this one particular transfer, cx is automatically decremented, so you don't have to write okay, cx, decrement cx or increase di. So those things will be taken care of by the rep ins b instruction, right. So that can be done. So this is one of the uses of ins operation. Similarly we have an outs operation. It is very similar to the ins. Only thing is here the data the port address, okay, is specified again by the same dx register, and the source address is given by dssi. So this is again a memory location, it is not an accumulator data, okay. So memory location, so from the memory location this data will be taken. So you have to specify from where the data is going to come, and it is going into a port whose address is given by here, okay. Now remember never does it happen that okay this data is taken from the memory and directly pushed into the port, okay. It cannot happen hardware wise, okay. Although this command is written like this, okay, so this is a complex command, but in hardware implementation, okay, the compiler will break this command. It will fetch the data from the memory, put it into some temporary register, and from temporary register only it can go to port, okay. That's how the hardware is implemented, okay. So don't just get carried away by these instructions. These are high level instructions, I could call it as high level instructions, which is given just to make the writing of the software a bit compact, okay. But 8086 doesn't really support direct memory to memory data transfer. Okay, so there has to be some register which comes into play in between. Okay, but that is not evident in this software. Okay, in this commands. Okay, so this is just to make the life of the software engineer a bit more comfortable. That's all. Okay, so this is again, right, so this is 100 data will be, again, if you see here, what happens is this port is specified, right, and SI, the data. So first some data from the memory will be taken and it will be put into the one port. Now again the same next data will be taken and it will be put into the same port. Okay, so so you have to find some application like that, right? But if you have a set of memory locations, a set of data in certain memory locations, and each data needs to go to different port, then you have to insert that command wherein the dx is also accordingly updated. Okay, after every move command, right? So that also you have to take care. Okay, so this is a small introduction to ins and outs. So we'll stop it here, and in the next class we will start with arithmetic operations. Okay, thanks a lot.